So we have the first dimensionless ratio to be delta P divided delta P multiplied by L to the 1/3 divided by mu times Q to the 1/3. Okay, it's an unconventional choice. If you look at the book, they have discussed the whole problem in terms of the fluid velocity, average velocity V, and not in terms of the flow rate. This is not wrong, it's just different, it's not something that's in the book, but I'll stick by this. Okay, and the remaining variable I have here is D, and obviously if I were to describe D, Q and mu would not be involved because it's just a length scale. So I'm just going to write this is D divided by L. That is my second dimensionless group. So having said that, what I have remaining here is that I have a relation which is delta P is a function of the flow rate, length, diameter and viscosity that has now been reduced to delta P L to the 1/3 divided by mu times Q to the 1/3 is equal to a function which we still don't know, of D over L. That is, if you did an experiment with, let's say, instead of 10,000 combinations, you did say 100 combinations. You had 100 combinations of flow rate, viscosity, diameter and length. To plot your data, instead of plotting it as simply delta P versus something like Q or mu or D or L, what you should be plotting is delta P L to the 1/3 divided by mu Q to the 1/3 as a function of D over L. What that means is you can vary any one of the four. You will automatically get a new value for D over L and for this parameter, and you would just get a graph that looks universal, independent of each variable, but it is a collection of all the variables. Okay, so we'll see more of this. That is, I asked the question, why do we need dimensional analysis? It is needed to reduce the number of independent variables. So instead of 4 independent variables, we have really one independent variable and one dependent variable. Okay, so that is the main goal of dimensional analysis.